Hi. So in the last lecture, what we did, we derived the expression for the cout for 4-bit adder, okay? And we noticed that for this expression, it grows linearly with the size of the data here. So you can see here that I have a gate, an OR gate, okay, which is on an order of n, and also an AND gate of an order of an n, and overall an expression of a complexity with an overall of the order of n, where n is the width of the data path. And we said that we don't like this. We need to find a better way because this is delaying my propagation to create the cout and making the adder, which is a fundamental operation, making the adder to be slow. So how can we speed this up? So obviously we can speed things up by doing parallel processing, by doing things in parallel. Let me just give you an example. Okay, let's go to the whiteboard here and let's give an example. Suppose um, I need to add x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7 plus x8. Now, currently, the way if we do this serially, meaning add x1, right? Then add x2, then add, then it will take to the order of n, okay, to do this complete addition. So I need, in this case, n minus 1 additions. So if I have 8, I have 7 additions. So you can see that this is addition number 1, addition number 2, addition number 3, 4, 5, 6, and 7 additions. So it's on an order of an n. So if I need to add, for example, 128 x's, then I need 127 additions. So the order is it is of order n. We don't like that. We need things to be faster. How? Well, I can do this by doing it in a binary tree fashion way. So I can add x1 and x2 together, and x3 and x4 together in parallel, and x5 and x6 together in parallel, and x7 and x8 together in parallel. Okay, then I can add these together, and then I add these together, and then I can add these together, and then this is the final sum. Okay, this is the final sum where of all these x's. Now, what's the delay here? Well, the delay is 3 add operation instead of what? Compare this to 7. So what's the order of this? Well, the order of this, it's the height of the tree. It's a binary tree, and the height of it is log of base 2 of n. Now, why base 2? Because I'm grouping by 2's. Okay, I'm grouping by 2's. I'm grouping by 2's, and that's why so this is much faster. So suppose I have, for example, 64 x's to be added. Well, I need a delay. If I go through a binary tree, it is going to be a delay of 6 additions. So now you can see by doing things in parallel, they are faster. Okay, and that's one hint of how to improve things. And we will go back here. We'll try to find out a way, a better way, where I can generate this expression, right? This expression which is growing linearly, right, in a better way. Okay, so let's see how we can do that. Okay, now what we could do here is that We will talk about something called group propagate and group generate. Okay, group propagate and group generate, and this is see if I So the group propagate now is a new expression that we will define. It's a group propagate and a group generate. Okay, so we have defined a group propagate and a group propagate and generate terms for just a single bit. And now we're going to talk about group propagate for multiple bits, not just a single bit. So now let's go to the whiteboard. Maybe we'll have a quick discussion there in the whiteboard and to illustrate some of the points. And okay, okay. Now, um, now, so the concept is very simple. Suppose I have, for example, suppose I have a range of bits, right? Okay. Let's see. This is bit one, bit 2, bit 3, and bit 4. And I have here, I'm adding A and B. And let's say here in these bits, for example, let's have certain values here, 0, 1, 0, 1, 1, 0, and let's see, maybe 1, 0, 1, 1. Now, we have indicated earlier, so these are this is bit position 1, bit position 2, bit position 3, and I split them purposely now, and you will see why. Now we can define something. Remember, recall, we had defined a generate for bit I and a propagate term for bit I, and we said a generate for bit I is what it is when A ANDed with AIBI equals 1, and a propagate it is when AI XOR BI equals 1. Now I will introduce the term of propagate or generate from bit 2 to bit 1. So I want to see if I can generate a carry from these two guys by adding just this block. So let me see. If I add this, the sum here, and this is the carry. So the sum here is 0 plus 0, a 0, 1 plus 1, it is what? It is a sum of a 0 and a carry of 1. So now the carry goes to the next stage. Now, what I can say about this, that from bit 1 to 2, I can generate a carry. Now, let's see if I can propagate from 2 to 1, meaning if there is a carry that comes in right at this block, can I transfer this carry? Well, this can be computed by simply saying, and for me, the p the propagate at bit position 1 with the propagate at bit position 2. Let's see, the propagate at bit position number 1, this is 0 exclusive or 0, so this is 0 ANDed with 0, which means 0. This means that this group of bits here, I cannot propagate the bit. So whatever carry comes in here as a block here, I cannot propagate it to the next stage. Okay. Now let's see here. I can repeat this process here where I can talk about what. Let's see. For example, I'm gonna change this, by the way, to let's say, for example, a 0. Okay. Let's now talk about the bits for this block for this block. I can talk about the generate for bit 3 and 4. Can I, when I add these two guys independent of this carry, assume I don't have a carry, can I generate a carry? Well, let's add 1 plus 0, it is a 1. 1 plus 0, it is a 1. No carry. I don't have a carry. Carry is a 0 here. Okay, so from generation from bit 4 to 3, the generation as 0 when I consider these groups of bits. Okay, can I propagate? Well, let's see. The propagation from 4 to 3 equals what? Well, it is the ending of propagation of at bit 4 ANDed with the propagation at bit 3. Let's see, at bit 4 it is what? 1 and 0, this is 1, 1 exclusive or 0. And then 1 and 0 here, this is 1, and therefore this is 1, which means I can, whatever carry in comes in here, I can propagate it. Now, here comes the very interesting part. The very interesting part, what I need from all of this discussion is I want to check if I can generate from bit 4 to bit 1. So given the information about bit 1 and 2 and 4 and 3. Okay, well, it turned out that I can generate from bit 4 all the way to 3. Notice that I'm merging now this domain. I'm merging that from 4 to 1 if I am, so this is here, oops. If I have a generate from bit 4 to 3, okay, if I can generate from here, or if I have a generate from here, generate from bit 2 to 1, and I was able to propagate it through 4 and 3. So let's review. I can generate this carry here if I for the entire bits from 4 all the way to bit 1. If I can generate, given the information about the 4 to 3 and 2 to 1, if I can generate the carry between 4 and 3 bits, or I have a generated carry from the previous bits here, which is 2 to 1, and I was able to propagate it. Okay, so let's take a look at this example here. Well, the generation here, it is a, from my computation, it is a 1. So this is 1. This one here, it is a 1. And this one here, it is a 0. Okay, right? So let's see, what's the value here? 1 and 1, 1 or 0. So this is the value of 0 equal the value of G to 3, G 4 to 1 is 1. Which means given this group of bits, I will be able to generate a carry. Well, let's add them to the side here and double check. So A is what? A is 0, 1, 1, 1, and B is what? 0, 1, 1, 1. Okay, and let's add them. So this is 0, 1, 0 is a carry here, 1, 1, and a carry out. Which matches what I have predicted right here. Okay, so the idea here that given the information about small ranges of bits, I can predict larger ranges of bits. That's how I can, in other words, let's take it the backward. Given a large range of bits, I can decompose it to a smaller range of bits. Given the generation of large range of bits, I can decompose it to a smaller range of bits, and I keep decompose it, and that decomposition is what makes the calculation faster and in almost like a binary tree fashion, okay, quicker and faster. Okay, so let's go back now to our slides. All right, so now what we are saying here in the slides, as we have seen in the example, that the generation I have now a smaller range of bits from I to all the way to J. I'm splitting it from I to K and K minus 1 to J. In the previous example, there was here bit 1, 2, 3, and 4. Okay, so I have, now we can say that I can generate the carry for the entire range here, okay, from bit I to J, given the information about the generation of a carry from I to K from this region, okay, or if I know that I generate the carry from the previous bits of information, previous range of bits, and I know that I can propagate it. Okay, all right. So that now you can see the large range of bits has been decomposed to smaller range, where it is quicker to compute the result, much like we have done in just the previous example. Recall when we were adding x1 8 times, what we did in the binary tree, we decompose it to just addition of two x1 and x2, and so we decompose this large addition into binary, into sort of like addition of two x's. Okay, that decomposition made it quicker and faster to compute the 8x's. Okay, so here in formula, what it is, the group generate from bit I to J equals the group generate from I to K, or group generate K minus 1 J, ANDed with P, the group propagate from bit I all the way to K. And you can generate the group propagate for the entire range by ANDing the group propagate for the period I to K and K minus 1 to J. So basically, again, I want to stress that what we are doing, we are decomposing the expression of large interval or large range of bits to smaller ones. And I can repeat here, I can have smaller ranges here of bits, and I keep doing this exactly like I can do for a binary tree. Now here is the base case. The group generate from bit I to bit I. It is the group generate for I, which is the ANDing of the ith bits for A and B, and the group propagate from I to I is the ANDing XORing of AI and BI. Group generate for bit 0, it's actually the CN, and group propagate for bit 0 is 0. Now I can compute the sum by exclusive OR of the propagate of the current bit, okay, and the group generate from the previous bit, because this is considered to be Ci minus 1, okay, and Ci minus 1, it is the same as generate the carry from bit 0 all the way to I minus 1, okay. Now what we are going to do is that we're going to introduce the PG logic. We will study the adders using PG logic, and this PG logic is very famous of constructing fast adders. The PG logic, the fast adders, and the skeleton for that, we will see that this adders using PG logic consist of the three stages. Stage one, number one, stage number, this is number one, stage number two, and stage number three. In stage number one, what we do, we create these propagate and generate for single bits. Okay, so for example, G3, it's the ANDing of A3 and P3, and the P3 is the exclusive OR of A3 and P3. And the second stage here is the generation of all the carries, that the intermediate carries that I need for the sum expression. Okay, remember the sum expression, sum of bit I equals the exclusive OR of pi exclusive OR what? Ci minus 1. And I know the Ci minus 1 equals the generation minus from bit 0 all the way to I minus 1. So this is C0, this is C1, this is C2, this is C3, right? So now notice that these C's are used to generate the sum. These three C's are generate the sum. So in this here, I use the PG logic. And here, what I do, I generate the sum using this equation. Okay, 3 steps. And it turned out for these adders, the very first step, which is this one, and the last step are the easiest. The tough part is here. This is where the tough part, stage number 2, which is generating all these intermediate carries. Okay, that's the tough part. All right. Now, um, of course, right now what we did, we decomposed these expression based on two periods, right? You can see that this is the entire range of bits. We decomposed it into smaller two ranges. You can go higher valencies, meaning that you can really decompose into much smaller ranges. So you can compose into 4 range of bits. All right, okay, and that will create for you much more sophisticated adders, which can be faster than just decomposing into two expressions. Okay, now for example here, you can see valency of 4. Notice the range here from I all the way to J. Notice I am expressing this using how many intervals? 1 interval, 2 interval, 3 interval, 4th interval. Okay, and now you can see this valency. We decomposed earlier. We decomposed this into 2 intervals. Now I'm decomposing it into 4 intervals. That's why we call it valency of 4. Okay, so for example, if these are bits from 1 to 15, this could be, for example, 1 to, for example, 16. Okay, so this could be bit 1 4, 4 to 8, 9 to 12, 13 to 16, and this will give me a generation from group 16, bit 16 all the way to 1. Okay, now in the previous valency of 2, to decompose it to these finer ranges here, I have to do 2 steps. Now I can do it in 1 step. I can decompose it into smaller. So basically I am doing all of this decomposition. Now which is better, valency of 2 or valency of 4? Okay, so here this is sorry, this is here, valency of 2. I've broken it into 2 ranges. This is valency of 2. Which is better, valency of 2 or valency of 4? And in these cases, you really have to simulate and find out the better solution. Okay, now we can use the PG logic to do a simple carry repel addition. Carry repel addition, where as we said here, in terms of the very first stage and the last stage, they are the same. Okay, nothing has changed. It is really the tough part. It is generating these intermediate carries. And here what we do, the way we'll do it, we will do it similar to the expressions that we have generated, sort of the carry. So recall that we said that for the first for carry number 1, we say that carry number 1 equals G1 or carry 0 ANDed with P1. Okay, that gives me G group generator from 1 to 0, and this is carry 1. So now I'll take this one and feed it off to the next stage with P2, or generate from this step. Okay, that will generate for me a group generate from 2 to 0, which is carry 2. And this carry 2, I can take it to the next step with the group propagate, okay, or with G3 to generate C3. Okay, so this chain here generate for me C0, I'm sorry, C0 already from Cn, by the way, C1, C2, C3, and eventually C4. We call this carry ripple, and the reason it's carry ripple because it's going like so. This is carry ripple. Okay, so carry ripple, it is going like so. It goes like from the CN, okay, from CN all the way here and all the way here and all the way here. Okay, so that's why we call it carry ripple. It turned out for this carry ripple, which uses the P logic, I haven't gained really much because the delay for this thing is equal the delay through these exclusive OR, okay, the delay through the exclusive OR, the delay through I'm sorry, or the PG here, the delay through the exclusive OR for the sum, and then I have here the delay through these gates. Okay, let me see if I have done lots of here. Let me just okay, and these are PG, the delay through these guys, and the XOR, the delay through these guys here as well. And then here, it turned out these gates, I call them and or. I have how many of those and ors? N minus 1, where n is the data width. The data width here, n equals 4. So in this case, when n equals 4, I have 3 of these, which is true, 1, 2, 3. Okay, so that's the total delay. So for example, if and for this particular adder, for n equals 4, this becomes the expression. Now for higher width adder, n16, then this becomes the expression. Okay, okay, right. Okay, let's stop at this point and we will continue the discussion in next class.